In this video, I'm going to show you some of the statistical methods to test the normality of the population of a sample. Okay, so the first one I'm going to show you is the Kolmogorov-Smirnov normality test. But before that, let us talk a little bit about the background of the statistical method. Or the introduction. So statistical tests for normality are more precise since the actual probability or the p-value will be calculated there. So test for normality calculates the probability that the sample was drawn from a normal population. In statistical methods, to test the normality, the hypotheses are H sub 0 is the sample data are not significantly different than a normal population, and H sub 1 is the sample data are significantly different than from a normal population. Okay, so methods used to test the normality of the data. So some of them are that I'm going to discuss here is Kolmogorov-Smirnov test and Shapiro-Wilk test. Okay, but there are so many. You can see D'Agostino's method. There are Pearson's test. There are Lilliefors tests. There are so many tests. Okay, you can search it and then study. But I'm not showing many methods. I'm just showing a couple methods here that are more frequently used. Okay, so the first method for the normality is the Kolmogorov-Smirnov normality test. Also, in short, it is called Ks goodness of fit test. Okay, this method uses relative cumulative frequencies for observed and expected data and their differences. The expected cumulative frequency are evaluated using the normal distribution. The following are the steps for the Ks normality test. So if you want to do it manually, so these are the steps that you do. Write down H0 and H1. For each observed frequency, first arrange the data in ascending order, like in the qqplot, okay? And find the expected frequency as follows. So how do you find out the expected frequency for the given observed frequency? Is first of all you find out x bar and s from the data. Okay, like find out the x bar and s from the data, from this data. And then what you do next is then find the cumulative relative frequency for observed data. So how do I find out the cumulative relative frequency? Is f sub I equals to I over n, where n is the total number of data and I is the number of data less than or equal to x. So how many data points are less than or equal to that value? That is we denote by I, and n is the total data points. I will show you how do you do that. Okay, and then next thing you do is after you do that, you calculate the G score for each observed data using G equals to x minus x bar over n, and then find the area left of G under the normal distribution using the P norm G01. Okay, these probabilities are the expected cumulative relative frequencies. So this is the observed cumulative relative frequency, okay, and this is the expected cumulative relative frequency. That will be the basically the area, okay, that will be the area under the normal curve, and then left of G. All right, so and then after you do that, you find out D sub I is the difference, absolute value of the difference of observed frequencies and the relative frequencies, and Di prime is you subtract the expected frequencies from, or you do the difference of the relative frequency of the next line minus the relative frequency of the previous line, okay, the previous relative frequency, and that's the absolute value of that. Okay, this is from the expected one. We will see an example and things will be clear. Note that the first value of Di prime is the first value of expected cumulative relative frequency, because f sub 0 is equals to 0, because we will not have f sub 0. The test statistics is the maximum of all Di and Dis, okay, using the sample size n, alpha, and Kolmogorov-Smirnov table. Find the critical value. You use the table. If you want to do manually, you use the table to find out the critical value. I will show you that too. The table, I will show you the table, and the critical value we denote by D and alpha. So if the test statistic is greater than the critical value, then reject H sub 0. Okay, if the test statistic is bigger than the critical value, then reject. It will be like a right tail test. That's why if the test value falls in the rejection region, we reject the null hypothesis. Otherwise, no. So the rejecting the null hypothesis will be same as rejecting this, meaning that they are not significantly different from the normal population, and rejecting that means you are kind of supporting this one, right? So that means the data are not normal if you reject. All right, so let us see an example, then you will see all the steps in this example. The following data represents the height of the trees above the ground where the moths were observed on a trunk of 25 meter tree. Xi represent the height and f sub I represent the frequency. So for alpha equals 0.05, use Ks one sample test if the moths are distributed normally from the ground level to the height of 25 meters. So what is happening here is they are counting the moths in every height of the tree. For example, if the tree is 25 meters long, they count what is the how many moths were there in the 1 meter height, how many moths were there in the 2 meters height, how many moths were there in the 3 meters height, and so on. Okay, so so this is the height and the frequency data that is given 1.4, 2.6, 3.3, and so on. So it is in the increasing order. So you see that what is the null hypothesis? The moths are distributed normally from the ground level to the height of 25 meters, and then H1 is they are not distributed normally. So the test statistic D equals to 0.1667. How? Okay, so what we're doing here is I'm finding the cumulative frequency. What is the cumulative frequency means? How many are there below that? So like that, right? So how many were at 1.4? There is only one. How many were less than 2.6? There were 1 plus 1, that is 2. How many were less than 3.3? 1 plus 1 plus 1, 3. So you are basically adding these. 1 is there, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 2 is 7. Oh, there is 2. At 5.6, there is 2. There is not only one, all of them. So it is repeated, okay? So, and then 5 plus 2 is 7, 7 plus 1 is 8, and so on. Okay, now, how do I find out the observed relative frequency? So how many are total? Total were 15, right? So what do? Is you do 1 over 15, 2 over 15, 3 over 15, 4 over 15, 5 over 15, and so on. This is the observed relative frequency. Now, how do I find out the G value? So the step says that to find out the G value, you do X minus X bar over S. What is the X bar and S of this? You find out those. So here the mean is 8.41. And then standard deviation 5.90. You do that, and then you do X minus X bar. So X minus X bar over S to find out these G values. Okay, for each of these X values, you apply that. All right. Okay, so after you find out the G value, what do you find out is you find out the expected relative frequency. How? You do P norm and then that G value. So P norm, G value, and then 0, 1 will give you that expected. Okay. So now next thing is you need to find out DI and DI prime. That is a little bit different there. So how do I find out DI is relative cumulative frequency minus the observed minus expected but absolute value. If there is a minus sign, you just remove that. Okay. So what do? This minus that and absolute value. This minus this and absolute value. This minus this and absolute value, and so on. This is what you get. Now to find out the DI prime, what you do is relative Fi minus 1 minus relative Fi. So what you do is, what is the relative Fi hat? That is the expected one, okay? So which one is expected? You do the first one of the DI prime will be exactly copy from here. You copy that one here, okay? For the second one, what you do is you subtract this minus, this is the expected one, expected minus the previous, from the previous line, the observed one. So expected minus observed from previous line, that goes to the second line. For the third line, you do expected in the third line minus a second line of the observed one. Okay, so you go one line, you subtract from you subtract to the one line previous, right? So it is like previous line of the observed. So expected minus previous observed, expected minus previous observed for each of those data points. And you write here, and note that the first one, very first one on the di prime is same as the expected, very first one of the expected. Okay, so after you do that, and at the end, to find out the critical value, or sorry, to find out the test statistic, what you do is you find out the maximum of those two columns. So what number is the maximum of all these? It sounds like the maximum on this here is 0.11, and on this column the maximum is 0.16. So the overall maximum of these two columns is 0.1667. That's how you find out the test statistic. Now to find out the critical value, you need to use this table. This is the Ks table. It is for the two-tailed test. Okay, so the Ks table in this case is, see, n is 15 because there are 15 data points. So this table is for n and alpha. What is our alpha? Is 0.05. So 15 and 0.05. This is 15, and what is the 0.05? Is 0.3376. You see that? Where is 0.3376 is the critical value. So is our test value is bigger than the critical value or less than critical value? Our test value is less than, right? See the test statistic, this is less than the critical value. We do not reject H0, meaning that the data are taken from the normally distributed population, or the sample is taken from the normally distributed population, or you can say that the sample follows the normal distribution actually. Okay, so so next thing that I want to do is I want to show you how to do the Kolmogorov-Smirnov test manually in R. Okay, so we will do exactly the same steps. All right, so this is the data point I copied from this data point. Okay, so I'm running that. I'm finding the mean and standard deviation of that data. Now what I'm going to do is I'm going to copy this height and then the cumulative frequency. So that's I give a name as data there. That's the height data. Okay, and I stored it, and this is the cumulative frequency. So how do I find out the observed relative cumulative frequency? It just divide the cumulative frequency by the total number of data points, that is 15, right? And that's what the observed cumulative frequency is. Now to find out the G value, what you do is you find out the x minus x bar over S, right? That's what the formula for S is, x minus x bar over S. So why I'm doing that, M is, see, to find out mean and standard deviation. So here I am not copying 5.6 twice. I'm just copying only once because we have just only once, and that is repeated 2 times. So I copied that and that one. But actual mean and standard deviation should be found from the original data. So I found that mean and standard deviation. I denoted by M and S1. So that's what I did. Okay, that is the mean and standard deviation there. Now to find out the expected, so what you do is you do P norm and then the G value, right? So P norm G value will find out the area left of those G values there. That is the expected relative cumulative frequency. Now to find out the DI is the difference of expected minus the observed and absolute value of that difference. Okay, that's what the DI is. Now we need to find out finding the DI prime is a little bit tricky, right? Why is that? Is because so first value of the DI prime must be same as that the first value of the expected. See, that's what I'm doing. So DI prime 0 means it is giving just the position or the location. It's kind of matrix form. And then what I'm doing here next is DI prime, the first of the DI prime is same as the first of the expected one. And from the second, third, what you do to find out the second value of DI prime, you do second value of expected minus the first value of the observed. For the third one, third value of expected minus the second value of observed. That's what we are doing here. So DI prime I for 2 to 14, I is equals to, what do you do? Is expected I minus the observed of the previous one, I minus 1. Okay, if you run this and then print the DI prime, that's what you get. And the last thing I want to do is find the maximum of DI and DI prime. You see that? These are the DI primes. These are the DI primes, right? Now the maximum of these two columns, which is the maximum number of those two columns, is 0.16699. You see that? 0.1667. Now to find out the critical value, again You do the same thing for the critical value. Just look at the table on the next slide. You see that we got the test value is 0.1667, and using the table with n equals to 15 and alpha equals 0.05, we got the critical value 0.336760. And since the p-value, since the test value is less than the critical value, we do not reject the null hypothesis, because the test value does not fall in the right side of the critical value. Okay, so we do not reject the null hypothesis. Okay guys, we don't want to do that, all those long methods. So what we want to do is, I want to do the ks.test. That's all you do. ks.test, the data is the data 1, right? Because that is the original data. So the data 1, ks.test data 1, and then p norm, and then mean equals to mean data, and SD equals to SD, standard deviation, and alternative is that one, right? Now, the idea here is, if you want to run this statistical test for the normality, you need to install that package. You should uncomment that, run these two lines, okay? Run this line and that line. Since I ran that line already, I don't want to run that again, okay? And then you call the library nor.test, and then go just to, you don't have to do all these many steps, okay? Just do ks.test. You will get, by the way, you see that there is a big warning. What does it say? It says that in the ks.test, you need to have a different data points, or the data points must be distinct. So you cannot have a repeated data set. It says the tides should not be present. Tides should not be present in the Kolmogorov-Smirnov test. So this is the one of the big disadvantages of this test, okay? So if the data is repeated, then you do not use that Kolmogorov-Smirnov test. You see that? Since our data here, the 5.6 was repeated, so that ks.test using directly, it uses it shows a warning sign there, okay? So that means that we should not use the direct method for the ks.test using R if the data value are repeated, okay? So I will but I want to just show, I mean, you are perfectly fine to use this manual method for the Kolmogorov-Smirnov test, for the normality. If you do it directly, the graphically, you see that the data points are close to that line, right? So again, so one of the things that we cannot say from the graphically is how far scattered data are we consider not normal, and how close they should be. So that's why we need the statistical method, right? Because the statistical method gives you the p-value, the probability, and then we can decide with more confidence. But if you just look at the graph, these two data points are a little off from this line, right? But is that like far enough to say non-normality, or they are close enough to say normality? So we don't know that, right? That's why we need the statistical test. Okay, now here we were not very sure about the p-value when you use directly this method, ks.test method in R. The reason is because there was a repeated value, okay, repeated data set, and then R is showing the error there. And again, if you want to use by hand all this code, copy and paste on your problem, you are perfectly fine to use the ks test. Okay guys, all right, so the ks test can be used for non-repeated data, again for the two samples too. So what I'm doing here is x is one sample, let's say, and y is another sample, and you can do ks.test x comma y, two-sided and exact equals null. So what you can do is, if you run that, you can see the p-value is greater than alpha, right? So meaning that these data are coming from the normal population. Again, so you don't have to do that. You can do one by one, normality of this and normality of that separately. That is perfectly fine, okay? But what it says is, if the data are not repeated case, So you can check the normality of the two data set at the same time using ks.test. Okay, so the next thing I want to do in the next video is I am going to show you how to test the normality of the data using a Shapiro-Wilk test, which is a very powerful test and can be used even if the sample data value, some of the data value are repeated. Okay, it doesn't have any problem for the repeated data set. Okay guys, that is the next thing I'm going to do in the next video.